Okay, so the next expression would be to give you the most general expression. So for a beam, for a non-symmetric cross section, comma, the most general expression for the normal stress is given by, and I'm going to switch color because that black is dying. So sigma normal equals sigma x will be equal to fx over a. And now plus a nice long expression my of I sub z times z minus I yz of y times y divided by I yiz minus I yz square. And I'll go to the line plus mz factor of I yz z minus I y times y divided by the same thing, I sub y, I sub z minus I yz square. Okay, and once again here, don't pay attention too much to this sign, because what would be for you the way to select the sign? Is that if it's in tension would be positive, if it's in compression would be negative, no? Okay, but you have to do that with the understanding. Okay, so also last time we finished the class by saying that where is located the neutral axis? The neutral axis is located where the stresses are zero, no? Okay, so let's look over here. So let's say for a symmetric cross section, neutral axis located at CG, center of gravity. So now for non-symmetric cross section, what can happen? So let's say, let me put here maybe a little example. So you can have here the I-beam. This one is symmetric, or you could have like a U-beam. All right. That's one. The neutral axis will be at the center of gravity. Okay. So now imagine that you have here the I-beam and you just have the force, let's say, on top. Okay. So how is this going to bend? It's just going to bend symmetric, correct? Or if you put the U shape, if you put a load up or down, it's just going to bend. Everything's going to bend the same way. Now, what's going to happen if you have a cross section, a non-symmetric cross section, and let's say you have an L shape? How can this bend? If you apply a force, let's say right at the top here, because you agree that the CG will not be located on the structure, no? So even if the force here is symmetric, this is going to bend, but at the same time is going to twist, no? Okay, so you need to find also what would be the twist of that cross section. So you could have, let's say the neutral axis could be something like this. All right, so but the procedure is always the same. In order to, for non-symmetric cross section, the procedure is going to be the same thing. What do you know about the neutral axis? Locate it. At location where the stresses are zero. Okay. So what does that mean? If the stresses are zero, the normal stresses are zero, that means that this expression here will be equal to zero. All right. So if I rewrite the above expression, so using above expression, we're gonna have 0 equal to okay, I'm gonna say here neglect f of x. So let's take f away, because that one does not affect really the, it's just the one that is normal. So we have my times iz times z minus iyzy divided by iyz minus iyz squared plus m sub z of iyz times z minus iy, or maybe I could put, okay, iy times y divided by iyz minus I square yz. Okay, so doing some basic algebra, you find over here that y over z will be equal to my iz plus mz iyz divided by mz iy plus my iyz. So basically you see that the denominator will cancel out once you equate one to the other one, and you put y over z. All right, so now we're going to see why we're doing all this stuff. Remember, what did we say? If you have an L cross section, you agree that the CG of this cross section is not going to be on the structure. So really, what's going to happen in real life is that even if you put the force here, this structure is going to bend, but at the same time, it's going to twist, not the L. Correct? All right. So how much will that twist? Basically, that's what we're going to determine now, because we notice that we're going to say here, if the angle of the neutral axis is expressed as. So basically what we're going to have is that if you have a structure where, let's say this is Y and this is Z, so the angle between them, let's say, is beta. By basic trigonometry relation, what do you know? Tangent beta is equal to Y over Z, no? So now you see why we have the expression of Y over Z. Or using previous result, the angle beta is given by, so the same thing as we had before. I'm going to use the blue, tangent beta, and it's the same expression as before, which is my iz plus mz iyz mz times iy plus my times iyz. So remember, this is for non-symmetric cross sections. Okay, let me do a little figure here. So here beta, if it's not clear, is the inclination of neutral axis. So if I do a figure, yeah, could do the L, but let me do like another one. So you have this one. Okay, so let's say the CG will be over here. This will be the CG line. All right, I'm kind of making it up. Probably will be a little bit lower. Okay, actually, it should be lower. If you think about it. But the important part is that this is not what's gonna important here. Is that really the one that will give you the neutral axis should be here at a certain angle, beta. All right, so don't get confused over here. I'm going to write it down, but so for symmetric cross-section, you can also have that angle. And we're going to see when, okay? Tangent beta. If the symmetric is cross-section, what does that mean? It means that IYZ is equal to 0. Which will imply what? If we take that equation, this will just give you my times IZ divided by MZ times IY. Okay, so what does that mean? All right, let's say you can still have a symmetric cross section like the I-beam, correct? But now what happened if you don't apply the load right at the CG? Let's say you apply the load over here. Yeah, this is going to create a moment, even though this is symmetric, meaning that IYZ will be equal to 0. If the load is not right along this line, what's going to happen? This is, in addition to bend, is also going to twist, no? So you see that this will create moments. So in that case, let's say probably the neutral axis will be something like this, where this will be the angle beta. So, okay, you can also have the inclination of the neutral axis if the load is not being applied at the center of gravity. All right, so let's try to do an example here. So the black is almost gone, so I'm going to start using the blue a lot more. That's cool. So example. So the problem is a standard steel C180 times 22 beam is subjected to a bending moment of 5 kilonewtons per meter. Oriented at an angle of 13 degrees with respect to the z-axis. Determine the bending stress at points H and K. Okay, and basically you have the figure over here. Of a C channel. Okay, so in this case, what would be The CG probably will be somewhere over here. So we use the coordinate system. This is the Y, this is the Z. And what it's saying is that the load, the moment, sorry, which is the load, so M over here is at an angle of 13 degrees. This is the C 180 times 22. B. So this one, I just went online. You see for this type of cross section, you don't have the figure here, but it gives you the dimension, BF, and so on. So for different ones, you have all the different sizes over here. It gives you the dimensions of the cross section, but it also will give you the moments of inertia. The I here will be what? This will be the IXX, this will be the IYY. But be careful, because on this figure that is not shown over here, it looks like the IYY will be our IYY, but the IXS will be our IZZ. Okay, so what I'm trying to say is that you can find all this stuff from the tables, even though we're going to do the calculations. Okay, so here we go. So the first thing we need to find, we're going to find what is the loading. The first thing we do is find the loading acting on the cross section. Okay, so I'm going to redo the figure here very quick, but we could use the one on top. So we have here Y. We have here Z. We have here the value of the moment is M equal to 5 kilonewtons meter. And we know the angle here of 13 degrees. So if we project this moment along the y-axis, sorry, about the z-axis, what we're going to get? Moment about z. If we project it along the y-axis, what we're going to get? M of y. So by using very simple trigonometry, you can find out that M of z should be equal to what? Should be equal to M. So what would that be? If we know M, the adjacent will be cosine of the angle, which is for us 13. So this will give us 5 times cosine 13, which I have the result is 4.87 kilonewtons per meter. And the My will be equal to what? M sine 13, which will be 5 times sine 13 degrees, which will give us 1.126 kilonewtons per meter. All right, so now we're going to go to the cross section. So for the cross sections, we're going to look at the geometrical properties. So cross section. So let's say for this cross section over here, the C channel. If we go to one of those tables, D will give you the total height of the cross section. This will give you the width, so B sub F of the flange. Then you have the thickness of the web and the thickness of the flange. So if we had one of those tables, that will give us that D is equal to 178 millimeters. B of the flange is 58.4 millimeters. Thickness of the web is 10.6 millimeters. And T of the flange is 9.30 millimeters. Okay, and in our case, remember that we are using the following reference frame. This is Y, and this is Z. All right, so just as a review, we're going to show you how to calculate the moments of inertia. So the first thing we need to do, which in this case is very easy, is to find, the location of the center of gravity. So first thing we're gonna do is center of gravity location. Okay, so the Y, I'm not gonna do it because what would be the Y located? Should be right in the middle, no? Yeah. So that one is so obvious that I'm not gonna do it. So Y location is at D over 2. So it's right in the middle. What we are concerned is that what would be the Z location? All right, I know you all know that stuff, but when you need to do it, then it's a different story. How do you find the moment inertia of this marker? You start putting your finger at different locations until what? Is balanced, no? So what happened? You do it until the location where there is no more rotation, correct? So you think about it, the CG is the point where there is no rotation. So you think about it, there's one general equation, which is called the moment created by the Z location, Z bar times the area of the cross section, needs to be balanced by the area of all the different components. So in this case, what could be different components? Could be the top flange, the lower flange, and the middle web. Okay, or this. Okay, and this from this equation. So this is you balance the moments, and from here, really, what this gives you is that Z, the location, is equal to summation of the Z location of the center of gravity for each one of the different components divided by the total one. Or you can write this into an integral form. You might be more familiar with it. That will be integral of z sub I dA sub I divided by the integral of all the different areas. Okay, so in our case, I'm just going to do a little sketch of this, a little bit magnified. So let's see what I have. So what I'm going to call here, this will be 1. We're going to break this into 2 different parts. So it should be 1 and 1 will be the top flange. And let's say this will be here in green. This will be the second one, the second part. And we already know that the Y location will be at D over 2. So we know this is D over 2 and D over 2. And what are we trying to find? We're trying to find at what location Z from here will be the neutral axis. Okay, if I take as origin this H over here. And again, the coordinate system here is, like always, Y and Z. So this is statics, guys, not even solids. So to review. So if you look at the equation, what do we need to do? We need to find first either the area or the location, but let's first find the location. So of 1 and 2, if the origin of coordinate system is here right in the middle, or I mean, is along this edge. So let's say it will be, so all right, so let me change this one here. I don't have other colors, so I don't want to mix too much. So it says this will be Y. This is Y. And really we follow this should be here, Z. Okay, so what would that give us? Let's do first the white part. So we use this equation. So let's use Z bar. Let's use this equation here. So let's try to first find what is the Z location for the sections 1 and 2. Should be basically B flange divided by 2, correct? So this will be B flange divided by 2 times the area of the flange, which is what? B flange times the thickness of the flange. Okay, so this will be this one here. And what will you have? These 2 flanges, one on top, one at the bottom. We have the same Z, no? So I can multiply this one by 2. I'm doing this one and this one. Now, I'm going to do the middle one here. Instead of the flange, I'm going to do the web. What would be the area of the web? Or first, what would be the location of the Z? Should be, we follow the same, will be T web divided by 2, no? Should be right in the middle of this one. And now what would be the area? Should be, so the total height minus, so D minus twice the thickness of the flanges, minus 2TF times TW. I'm not writing too straight over here. Sorry for that. And now we need to divide that by the whole area. So the whole area is what? Is simply the area of the red one, of the two ones, which is 2 times BF times TF, plus the area of the middle web, which is D minus 2TF, basically this term, times T web. Again, this is for 1. This is for 2. And if you do the calculations, you find that Z. Oh, actually here we need to be careful because, I mean, it's the same thing, but since I use Z going in that direction, this should be actually what? Minus BF divided by 2, and this one should be minus TW divided by 2. So this should give you minus 14.6524 millimeters. So basically, that distance over here from the edge to here, since the Z is positive going that direction, will be negative 14.6524. Okay, so center of gravity, we found the Y location is over D over 2, Z location is this one. Now let's find the moment of inertia. So let's find moments of inertia. Okay, so once again, always we need figures, okay? Without figures, you cannot do anything. So we just plot again a small figure of the cross section. So now we know the CG will be here. Let's check, this will be the neutral axis. We assume the moments are being applied at the CG. This is the 2 over here. This is the 1 and the 1. And remember, our current system is, like always, will be Y and Z. Okay, so what is the physical meaning of moment of inertia? We talked about it last time. So what does, for example, if we start with IZ, what does IZ means? What does the quantity IZ means? I'm not talking about his name. Physically, what does it represent? Resistance to rotation about that axis. Okay, perfect. So it's how much this is going to resist to rotate about the z-axis. Okay, all right. So if you look at it, is section 2. Let's start by section 2. Is section 2 what's going to happen? Section 2 is we can calculate what will be between the section 2 about the neutral axis, no? Okay, so if you remember, for something rectangular, what is the moment of inertia given by? Is I equal 112 base HQ for something rectangular, no? All right, so what will you have for the second one? So for section 2, that will be equal to what? Will be equal to, so IC will be equal to 112. What is the base? The thickness of the web, no? TW. And now the height cube, we say, will be D minus 2 times thickness of the flanges. Maybe I did not need the bracket, but right here to the cube. So again, this is for two, because the CG of 2 is located right about the z-axis, correct? Now, what will be the I using this equation of 1? What would that be? Would be 112. Now, what would be the base? Would be the whole thing, which is df. And then what was the thickness? T sub f cubed. So that's it. Is that correct? No, because what happens is that you see this one is located at a distance over here, no? Yeah. What is that distance? So from here, that distance is d over 2. If you want, we can put here, this is T flange. I mean, this whole length here was whatever, B flange. I mean, I don't want to put too much, but again, you know, you can put as much as you want. So now what do we need to do? We need to use the parallel axis theorem to do what? To move this moment of inertia, which is calculated about here, to move it to the same location over here, no? So how do you do that? Is moment of inertia means what? Parallel axis theorem is what? I prime equal to I about the axis, so the original one, plus AD squared. This is the parallel axis theorem. So what would be the area? Let's just do it for 1. What is the area of 1? Is BF times TF. And what would be the distance from the center of this to the bottom? Will be D over 2 minus T flange over 2 squared. Okay, this is statics again. All this should be a review. But now what happened? We have 2 of these areas 1. So what can we do? Just multiply everything by 2. And again, this will be the moment of inertia for 1. So it gives you a moment of inertia about the z-axis equal to 11.314 10 to the 6 millimeters to the 4th. Okay, so similarly, if we do the IYY, or I just call it IY, so now be careful. What would that be? So IY. So now we are looking about the rotation about what? About this axis or about this one? We're looking about how this is going to bend about this axis, no? So be careful, because now all this is going to be switched, no? The B and the T. Okay, the base, before looking with respect to this one, now we're going to look with respect to this one. So as before, let's start by the second one if you want, by the area 2. So what would be the moment of inertia? It would be 112. But this time, what would be the base? If we look at how this is going to bend with respect to this one, what would be the base? The base will be that distance over here, no? Okay, which will be D minus 2 times T flange. And this time, what would be the height? The thickness of the web. Okay, so this is about this axis over here, no? Yeah. So do we need to move it? Like I was saying before, when we use the parallax theorem, D was the y direction. So now when we do the y, the distance, we need to look at what is the distance between the CG of this cross section to the general CG. So we found this one here. Now we need to move this one right over here. So what would that be equal to? So it would be plus the area, which is what? D minus 2df, which is the height, times the web. So this is the area. Now, what will be the distance between the center of this one to the CG? Do we know that distance over here? What is all that distance over here from here? This is Z bar, no? So the distance from the CG of this one here, from this just element 2 to this one, would be equal to what? Would be equal to Z bar minus T web divided by 2 squared. Okay. So again, all this is for two. Now we're going to do the same thing twice for one. So we find what is the IB about the center of these two cross sections. That would be equal to what? Plus 112. And probably we need to multiply this one by 2. So this time, what would be the base? Will be T flange. And the height will be B flange to the cube. Now we need to move it from where? From the center of this one, let's say will be here, to the general center of the CG. So that will give us what? So the area will be what? Will be BF times TF. And what should be the distance? What will be the center of the CG of this cross section will be located where? Will be just BF over 2. We'll have BF over 2 Here, be careful now, minus Z bar, but be careful here because I think I'm gonna just put minus Z bar. And here this will be square. And since there's two of them, we need to multiply by 2. Okay, so I'm gonna put it on the figure here. Be careful because I put the Z positive. So in our calculation, the Z is positive and is equal to 14.6524. Okay, I'm just taking the magnitude now. And all this will be for 1. Okay, so now that we have the loading, we have the moment of inertia, let's try to find the location of the 2 points so that we can go to the stress equation and apply it. So 627. Okay, so we're going to just look here. This is going to be very quick. Location of H and K. Okay, this is easy, but it's very important. All right. So again, we have our cross section. So I redo a figure. You see, I do a lot of figures. And sometimes I do multiple times the same figure. Okay, so where is our origin? The origin will be at the CG that we found initially, no? Okay, and this line also will be the whatever neutral axis, but let's just leave it at the CG. So we know this is Z, this is Y. Points H is that corner over here, is the top corner, and K on my figure, I don't know what it is, but let's put it over here. So here, and let's say here, okay? So where would be H located? What would be the Z? Where is that located? What would be the Z? Should be the Z bar that we say was equal to 14.6524. And what would be the Y? Would just be D over 2. Okay, we know all this here is D. That distance here, this is Z bar. So we know point H and point K. Okay, that would be a bit more, the Y would be a bit more difficult. What would be the Y location of? No, the Y would be easy. The Y, sorry, would be the Z. The Y would be what? Again, will be D over 2. I'm not putting positive or negative. I'm just looking at magnitude now, okay? If you want, you can put negative D over 2, but it's not that important. And what would be the Z? Z will be negative, but would be equal to what? Would be equal to BF minus Z bar. And actually should be the negative value of that, if you want to use the negative value. And I don't have that value. Unless you tell me how much is BF was equals, because maybe somebody can do the calculation. BF is 58.4. So 58.4 minus 14.6524. minus 43 point. Say that again.
747.
747. And maybe, I mean, this one probably I can do it. And D in our problem was equal to 178. So that would be, so 85, 87, no? 89? Okay, I don't know what I'm doing wrong. So let's say here 89. Yeah, it's 160 plus 18, correct. So 89, and it will be minus 89. But again, it's dangerous if you start putting signs. All right. So now we're going to calculate the stresses, which is why we did all this work. So what type of cross section is this one? Is this a symmetric or not symmetric? This is a symmetric cross section. Okay. So the expression for the stresses that we have is sigma normal stresses or sigma x. I'm just going to copy the same expression from before. I'm going to copy the one with the sign, but we don't care about the signs. Minus mz times y divided by iz plus my times z divided by I sub y. So I know these signs, but like I say all the time, forget about the signs because it's very easy to do mistakes. So what we're going to use ourselves as a sign convention is what? Tension is positive. And compression, we know, is negative. Okay. All right, so let's look at, let's say it doesn't have to be that way, but let's say this problem is, can't leave it just just for the visualization. Let's say this is our beam. Okay. So we know our current system is what? Is y, x, and z. Okay. And our cross section is again, so I just did it, but I'm not going to redo all of it. It's this way here, in which we know that this is y, and this is it. Okay. All right, so let's look first at point H. Well, point H is right here. Okay, so now I want you to think a little bit. The moment mz, and then we're gonna have a moment on mz, and we're gonna have a moment about my. Okay. So if you apply a positive mz, which is, what does that mean? Is it going up or down? What would be a positive moment? Is counterclockwise, no? So if you look about moment about the z, this will be bending in what direction? Kind of this way, no? So if it's bending that way, H will be in tension or compression? H is the top. will be in compression, no? Okay, so this will give us here compression. So if it's compression, basically we need to start thinking that then the stress should be negative, no? At that location, yeah, due to mz. So the stress due to mz should be negative. Now my will mean what? I mean, he's a bit more difficult, but I mean, not more difficult, but now this will be bending in what direction? My, this will be counterclockwise, so will mean it will be bending inside the page or outside. Should be bending inside. So if it's bending inside, what will be point H? Will be in tension or compression? Be careful here because let's see, maybe I don't know anything about it. So now we have this bending, this is positive, so this is bending in that direction. So which way do we put this one? So yeah, should be wait here. I put a. I'm just looking here. No, I'm looking here. That I forgot an R on compression. Okay, I was just paying attention to that instead of the figure. But basically, I think you are. I think you're right. But let's. I think we forgot to look at something first on the figure, on the initial figure, which we should have paid attention. I'm just paying attention now. So page. So on this page, due to this moment, basically what do we have? We have mz is positive, but my is negative, no? Okay, so the way I plot it. So if that is the case, that means that actually we're gonna have the reverse if the moment is going clockwise, no? Yes? So which actually will mean that is bending in the other direction. So this will be going, instead of in, will be coming, I don't know how to do this, like out of the page. And in that case, point H will also be in compression. But you were absolutely right before. If my goes counterclockwise, H will be in tension. Okay? All right, so we can do the calculation for point H. So let's say here, we can say that stresses at H. Let me just rewrite the general equation again, minus mz times y divided by I sub z plus m sub y times z divided by I sub y. Oops. I think I also forgot to give you something here now that I can. Yeah, so I run out of space. Sorry for that, guys. It's not that important, but since I have the value here on page 26, we did the calculation here. We did everything, but I did not give you the value, no? All right. So maybe write it down here. This will give you that I sub f sub y is equal to 0.70222. So before I give you, okay, 10 to the 6 millimeters to the 4th. So all that, so I can now substitute into this equation. All right, so we're gonna say here, be careful here, because remember, we don't care about those signs anymore. We know that these both are in compression, no? Okay, and both gives compression. So what was the moment for MZ? If I have it here is 4.87, is that correct? Kilonewtons per meter. So this will be 4.87, 10 to the 3 newtons per meter. You want to put here newtons per meter so we can follow the units. What is Y for point H? We had it, so point H, the Y that we had before is equal to 89. So be careful here, we're going to meters. So what would that be? Would be, if we have here, how many meters is 89 millimeters? What do I need to multiply by? 10 to the negative 3. So that's good. They'll cancel each other. Now this will become meters. And now be careful with this one, because IZ was equal to what? 11.316, 10 to the 6. What? Millimeters to the fourth, no? Yeah. So how will you go to millimeters to the fourth to meters to the fourth? What is the difference between millimeters and meters? What do we, I mean, you just had it here, would be what? 10 to the minus 3, no? Correct? And now what do you need to do? This is for 1 millimeter. So if it's to the fourth, multiply by 4, no? So it will give you minus 12, basically. So this would be for the first term. And I'll put here plus my, things was given by 1.126. So 10 to the 3. So this will be now meters to the fourth over here. So Newton meters again. Times, I think here, now what do we need here? Now we need the Z for point H. Z for point H is 14.6524. 14.6524, 10 to the minus 3 to go to meters. Divided by the I sub Y, which we say was equal to 0.70222, 10 to the 6, and we do the same thing over here, times 10 to the minus 3 to the fourth. This will give us to the fourth. And if you do the calculation, this will give us that sigma H. So here you have two choices to give me the result. So that gives me actually 61.8, 10 to the 6 pascals. So you have two choices. H, it will be in tension or compression. It will be in compression, okay? So the preferred way that I like more is that you give me, this is equal to 61.8, 10 to the 6, which is actually equal to 61.8 megapascal, and you write down over here compression, or what can you give me? Or you could just rewrite sigma sub H equal to minus 61.8 megapascals, and I will understand that the negative sign means compression. Okay. Okay, so now similarly, we can do point K, but it looks like I don't have the results for point K. So maybe, so you have to do calculations for me, but let's just do it. No, I have them, they're here. Good. So point K, let's see if we can finish. So for point K, again, I redo the figure very quick. All right, so we had Y equal to minus D over 2 and Z equal to minus BF minus Z bar. Then we had the values, but it doesn't matter. So we follow the same reasoning as before. So this time, let's use the figure as before. So basically, if K is at the other side, we're gonna have the same thing as in this case, but the bolt will be in tension, no? Does that make sense or no? Why was it here? If this is bending up, what does that mean? Is that this area is up, so this side is compression, this side is tension, no? Okay, and you will have the same issue where you have the bending out of the page. So basically, since we run out of time, we know this will give you tension. And this one will give you tension. Okay, so if you substitute into the equation, sigma sub K equal to mz times y divided by iz plus my times z divided by iy, you get that sigma sub K is equal to 108.4 megapascals in tension. And this should be page 29. Okay, and finally, so that's why we did all this example. Is that, so the last thing we need to do, since we have the moment my, mz, all right, will be the angle, all right, the angle beta of the neutral axis. So if you remember, the equation was tangent beta equal to, for a symmetrical section, my I of z divided by mz I of y. So here, since the moment, this one was negative, minus 1.126, times whatever this one is, 11.314. The units will cancel out, so we don't need to worry too much. This is unitless, it's an angle. 4.87, 0.7022. This will give us an angle of minus 74.95 degrees. So what does that mean about the neutral axis? Is that if we have our cross section like this, so we knew the location of the CG was so we knew this was the CG here. So what does it mean about the neutral axis? The neutral axis will be at an angle of what? Of 74.95 in that direction. So you see the stresses, I mean, I don't know where it's going to cut, but the stresses would probably be 0 here and 0 over here. No, it should cut. This is almost 80, so probably goes more up and down. I guess it will be here and here somewhere on the two flanges, the bending stresses will be 0, no? Yeah, because that's the definition of the neutral axis. But obviously I did not plot it properly. So again, what does that mean? Is that if you apply those moments to this cross section, even if you apply them at the CG, how is this going to bend? Is it going to bend just straight down? Is it going to bend just on the y direction, or is it going to bend and kind of twist? It's going to bend and kind of twist, no? So let's say if somebody was asking you to find the total deformation, so let's say you knew the Z deformation and the Y deformation. I mean, doesn't matter if you put here direction. What would be the total deformation? Y squared plus Z squared, no?